Hello, everybody. Good afternoon or good morning. It's just 1 o'clock Eastern now, so I think we should probably get started. So welcome everyone to a research workshop on secure IoT hardware. I'm Hugh Pottsmith from CMC Microsystems. Thank you for joining, and thanks in advance to the speakers for contributing their time and energy to contributing to the workshop. In terms of agenda, I'll give a quick introduction to CMC, mostly as a buffer to let people join the workshop. And then we'll get started into the program portion of the agenda. We're targeting a 3-hour time frame with some time at the end for open discussion to sort of help CMC or guide CMC in what we can do in providing some of the infrastructure and some tools and technologies in this area that can help researchers in our network. So as I mentioned, I'll give a quick introduction to CMC. For those who may not be familiar, CMC Microsystems is a not-for-profit. We were founded in 1984, and we're the manager of Canada's National Design Network, and I'll talk about the CNDN in a moment. But we're largely an infrastructure provider for research innovation in a number of microsystems technologies, including microelectronics, photonics, IoT, and edge AI or embedded systems, MEMS, nanofabrication and integration technologies, as well as quantum computing. We are manager of the Canada's National Design Network, and this is a collaboration between 65, or I think more than 65 universities and colleges across Canada, connecting 10,000 academics and 1,000+ companies with which they're collaborating to design, make, and test micro and nanosystems prototypes. Annually, we work with over 1,000 professors and up to 10,000 students using CAD tools and manufacturing devices and testing those devices. We measure our success through the outcomes that the research community develop with the technology we provide. So in the past year or last year, that includes over 4,000 publications and 150 research awards and patents, 80 patents awarded, 430 collaborations with industry, startups, 14 new startups, and 610 HQP moving to industry with the skills that are developed through their research, postgraduate research primarily. The infrastructure we provide is binned into CAD, Fab, and Lab. In terms of CAD, we offer CAD tools for designing, simulating, and making ready for manufacture devices, systems, sensors, all sorts of technologies. As I've mentioned, the CAD tools are provided either on site, installed on site, or in a secure distributed private cloud that's managed by CMC. We also provide user guides and training and process design kits to make these devices ready for manufacturing, which leads to the Fab services we offer. So we offer multi-project wafer services in technologies from microelectronics down to 12 nanometer, silicon photonics, MEMS, nanofabrication, including at nanofabrication labs at universities across Canada. And we offer support to ensure that the researchers get their devices manufactured right the first time, and then also offer the packaging and assembly services so they can mount them on PCBs or get them put them in use test equipment to validate and characterize the devices. And then we offer lab equipment through our equipment loan pool for test equipment, FPGA development platforms, and things like that. We also offer open source platform technologies through our GitHub repos. We also do technical contracting services and offer services such as quantum coding for the access to the quantum computers that we offer. We also help to construct research networks and develop international partnerships between the researchers, industry, and our partners and suppliers across the world. So those services are primarily to researchers in Canada. We also offer a subset of those services to startups through a virtual incubator environment. So that includes CAD, fabrication access, as well as some of the lab equipment and resources that we provide to the academic community. In terms of embedded systems and IoT, we have a number of offerings for RISC-V processor design and prototyping. We're a member of the Open Hardware Group, which is a Canadian not-for-profit that offers access to a number of RISC-V processors that are verified to an industrial standard and designed for manufacturing in either on FPGAs or in fabrication technologies. And we're working on a project with Open Hardware to manufacture a 32-bit RISC-V microcontroller in GlobalFoundries 22 nanometer that will be going for manufacture later this year. There's also work going on 64-bit processor, as well as a vector scalar processor accelerator for a 64-bit RISC-V. And so along with Open Hardware Group, we also offer the similar design kits for fabrication and the multi-project wafer services, so that researchers can take these platforms and develop their own custom prototypes, add their own accelerators, and those sorts of things, and get them manufactured and put on boards and packaged and assembled. We also offer an open customizable IoT sensor platform, which has a Bluetooth low energy microcontroller, a number of off-the-shelf sensors, and full design views and code, so that anyone can take this platform and customize it for their own applications. And this is also available in CMC's GitHub. And then we offer a number of services or products and services for research in artificial intelligence in the cloud, a number of accelerator clusters for AI training and inference. We also offer tools from deep light to optimize the neural networks for embedded processing. And then we offer access to edge processing capabilities, such as FPGA development platforms through our equipment loan pool, so that these networks can be deployed at the edge. And we have a web page on AI and machine learning that goes into more detail on a lot of these products. And just let you know what's coming up beyond the current workshop. We've got a training, extended training course on Cadence analog mixed signal design methodology and FinFET layout training using GlobalFoundries GF22 LP technology. This is March 7th to 18th. As well, complementing the AI infrastructure that we provide, we have a accelerating AI workshop. This is, I believe, the third annual workshop that we've organized, and it's got you can check our website for the full program, but it's a half day workshop with a good program for looking at sort of accelerating AI applications, both in the cloud and at the network edge. And a number of upcoming events: Photonics North, Nano Canada, Newcast in Quebec City, and the Texpo student demonstration competition is also affiliated with Newcast this year. And there's more details on the website. So thanks. If you have any questions on anything I went through quite quickly, please let me know. And then I guess we'll dive into the workshop itself. So just a couple bullets of context, why CMC's looking in this area and looking to offer infrastructure in the area of secure IoT hardware. So with the rise of IoT and AI and ML and 5G, there's a great demand for power efficient, secure computing at the network edge. A lot of the applications, IoT applications such as wearable biomedical monitoring, autonomous driving, precision agriculture require protecting user data as well as ensuring safe operation, both to human life and to essential infrastructure. And we're talking about billions of connected devices, and each of these devices represents a potential access point for security breaches that could either expose personal information or cause injury to life or infrastructure. So, a lot of these demands require new architectures for embedded processing, and these could be in the form of custom accelerators to handle both the security as well as the power requirements, and then new algorithms as well, both for security for AI and ML and the applications that are running on these platforms. So at the end of the day, we'll have a short discussion session, but some of the questions that would be useful for CMC to take away from this workshop is, what are the grand research challenges that this research community can address, and what are the infrastructure needs to support research in this area? And as I mentioned, what are the CAD tools? What are the fabrication technologies that are needed or that would be useful? And what are the lab resources? What test equipment or open platforms, research networks that could be developed? And associated with the infrastructure, what are the training needs specific to hardware security? Are there common platform elements that a large portion of the research community can make use of, that CMC can either buy off the shelf or develop in collaboration with researchers and with industry? What is the role or the advantage of open source hardware such as RISC-V or other platforms? And in addition to open source hardware or RTL level, if you will, are there other IP requirements that would be useful to this community in the form of analog mixed signal or security specific cores? So I guess we'll go into the program portion. So the first speaker is Dr. Padabiraman is a professor of electrical and computer engineering at UBC. He received his MSc and PhD from University of Illinois at Urbana-Champaign in 2004 and 2009, and spent a PDF year at Microsoft Research in Redmond before joining UBC in 2010. His research interests are in dependability, security, and software engineering. He's won multiple awards, such as the inaugural Rising Star in Dependability Award in 2020 from the IEEE and IFIP, Distinguished Alumnus Award from University of Illinois, CS Department in 2018, and 3 awards for excellence in research and mentoring from UBC. He's a senior member of the IEEE, a distinguished member of the ACM, and vice chair of the IFIP Working Group on Dependable Computing and Fault Tolerance. I guess I'll turn it over to Karthik.
Great, thank you, Hugh. Can everybody hear me?
Yes.
Okay, perfect. All right, so I'm going to share my screen. Okay, everyone can see it, I hope.
Yes.
All right, great. Thank you, everyone. So I'm going to be giving a broad overview of some of the work we're doing in my group in the area of robotic vehicles. And I know the theme of this workshop is on IoT edge computing, and in our view, robotic vehicles are a great platform to experiment with many of these edge computing issues. So the title of my talk is Detection is Not Enough, Low-Cost Attack Recovery. And this is mostly work done by my PhD students, Preetham and Zita. So I don't need to stand here and convince you that autonomous systems are the future. So they're increasingly used in real-world safety-critical contexts. Self-driving cars are here. Many of us have probably heard, or some of us may even have ridden in them. There are home robots being increasingly deployed, and drones and other kinds of robotic vehicles. So this is all great. Unfortunately, the future is not all unicorns and rainbows. In fact, there have been numerous instances of safety violations in autonomous vehicles, notably the Tesla and the Uber cases. There have been news stories about drones being used to attack targets, hackers getting into cars and stealing vital information, and so on. So all of this portends a very bleak view of autonomous systems unless we look at security from the get-go. So the focus of what I'm going to talk about today is specifically on robotic vehicles. So robotic vehicles are used in things like agriculture, warehouses, package delivery, and even in things like medical, rushing medical supplies. Recently, there was a news article about someone who was saved from a heart attack by a drone delivering a defibrillator to him just in time. So these are used in many safety critical contexts. Now, one of the key features of robotic vehicles is that there are a lot of sensors on board, and these are responsible for mostly autonomous operations. So I'm going to talk mostly about autonomous robotic vehicles, not the ones where you have a human operator remote controlling them. So these require sensing the environment to decide what is the best course of action. For example, in an autonomous vehicle, you can say, there's an intersection coming up, turn right in 50 meters. Or in a drone, it says, okay, the roll rate is so much, maybe it's going too fast, we need to slow down. So these are examples of sensory perceptions. Unfortunately, these are also points of attack against these robotic vehicles. So there's been many reported instances, or at least by researchers, who have shown that you can spoof these sensors quite easily. So GPS spoofing is probably the most common attack, where you spoof the position of a vehicle into making it thinking it's in a different place. You could also do this, for example, with gyroscopic noise. If you don't want to invest in a GPS spoofer, with a low-cost oscillator, you can actually make drones crash. And in fact, there was a very nice paper in Usenet Security 2015, which shows this is possible even at large distances. So these are real attacks, and we have to be cognizant of them. So you might ask me, has this ever happened in practice? Unfortunately, the answer is yes. So there was a famous Iran-US RQ incident where a drone strayed from its path. And in fact, recently there was another attack on near a Russian naval base where a warship was shown to be in a false location, again, with GPS cyber attacks. So these have been reported in the media, and so I'm guessing they're only the tip of the iceberg. There are many such attacks. Now, drones are being used in many civilian missions as well. So recently there was a news article about drones being used in organ transplant between hospitals in downtown Toronto. So I let you imagine the consequences of something like a cyber attack on a drone there. So that's something we absolutely want to avoid. So this problem has been addressed by prior work. There have been a lot of papers in the last 5 years trying to detect attacks in robotic vehicles. So notably, there are two classes of techniques. There's invariant-based detection, where you try to formulate invariance based on control theory and so on and monitor the drone, or model-based detection, where you try to model the environment and then say, is the drone or robotic vehicle straying from that model? Unfortunately, these techniques focus purely on detection, and they're very good at detecting attacks, but that's not enough. So why is that not enough? So let's assume that a drone is flying along a straight line path here and an attack is launched. By the time the attack is detected, what we have seen is that it's often too late. The drone has either sufficiently been destabilized or strayed off its path too much that it's not viable to take action by a human operator, for example. So crash is often the result. Or in some cases, you have hardware fail-safe and the drone might land. But imagine if this was being used in some critical operation, you probably aborted the mission and maybe even compromise the physical security of whatever the drone was carrying. So this is an issue which comes up, especially when you look at drones being used in war zones or even things like civilian missions where where lives are at stake. So you absolutely want to ensure the mission is successful. So now let's get a little bit deeper into what's the root cause of these attacks. So again, I want to be clear, I'm focusing on commodity drones and robotic vehicles. So in fact, later on in this talk, I'll show you some pictures of the robotic vehicles we use in our lab. None of them cost more than a couple of $1,000. So you can buy these on eBay or Amazon. So they're not probably the military grade drones or anything like that. Okay. So most of these robotic vehicles use what is known as PID controller, which is a proportional integral derivative controller. And what they do is they correct errors by monitoring using the sensors how far away the drone is from its expected trajectory and correcting it. So if you look at a PID controller, what it does is so let's say the drone starts in a certain position. Let's say a gust of wind moves it off the path. The PID controller will detect it, send an actuator signal, and lo and behold, the drone gets back onto the path. So this is the basic mechanism in many of these robotic vehicles. Now, this is all well and good if it's a natural disturbance like wind. So now let's see what an attacker can do. So here I'm assuming the attack is launched at multiple locations. So the attacker is able to control the timing and the magnitude of the attack. And just to keep it simple, we assume single sensors here. So there's a drone that's flying, the attack is launched at the time t equals 25, let's say. So the drone deviates from its trajectory. So no problem, the PID controller is active. The PID controller will try to bring it back. But remember, the PID controller is reacting to the attack, right? So it's going to overshoot the trajectory a little bit. So it's going to take the drone a bit away, which would be fine if it was just an error because it will bring it back eventually. But now the attacker is going to be clever, right? They're not going to stop right here. They're going to launch another attack. And you can do this easily with the sensor. So now the drone gets taken further away. So the PID controller is really working hard. It's trying to bring the drone back, and it's causing a large deviation because it thinks its previous actions were not successful, and it's going to cause a sharp turn, and boom, the drone crashes. So this is not a hypothetical scenario I made up. We've actually seen this, even at the cost of destroying some of these robotic vehicles, where we do these attacks and the robotic vehicle crashes. So the takeaway here is that PID compensation may be great at handling faults, but it's not so good at handling attacks. And that's the focus of the research that we're going to present. So what do we want? If you take a step back in a recovery technique, we want to be able to handle persistent errors of the kinds I showed you. Here, persistent error is an attack because the attacker is doing this over a period of time. So we want to handle erroneous physical states. And ideally, I want to prevent that erroneous state from reaching the actuator. The actuator is the one that powers the drone, the motors and so on. So these are the recovery requirements that we set out as targets. So the key innovation in what we're going to do is we're going to replace the feedback controller, which is a PID controller, or rather we're going to augment that with what is known as a feed-forward controller. So feed-forward controller, unlike the PID controller, which is going to measure and then react, the feed-forward controller is going to project forward. It's going to predict where the drone is going to be or the robotic vehicle is going to be, and then take corrective action even before it strays from the trajectory. So that's the key difference between feed-forward control and feedback control. Now, I'm not a control theorist by any means. So this was a concept we borrowed from control theory literature going back at least 2 decades. But the traditional wisdom in that community has been feed-forward control doesn't quite work unless you have a very accurate model. So it was sort of abandoned, or not really abandoned, but it fell out of favor with PID and feedback control becoming the dominant model. But as it turns out, feed-forward control is great for attacks if only we can come up with an accurate model. So how do we do that? Yeah, we use machine learning. So this is the modern equivalent of trying to find accurate models. So we say, look, let's throw all the parameters we have into this black box and use LSTM. And I can explain why later if you're interested. But we experimented with a bunch of different models, and that turned out to be the most the best for our purposes. So what we do is we look at all the possible values. We use feature set selection, come up with a set of critical features, the reduced feature set size, so we can run it on the robotic vehicle, and we use LSTM to find correlation. So here we're trying to the key idea is we're going to correlate past state with potential future states. So when we plug this in, so we're using the feed-forward controller here, which is going to be running in parallel with the feedback control. And what it's going to do is, when we detect an attack, we're going to switch to the feed-forward controller. So the feed FFC takes over at the time the attack occurs. So we're using all the early attack detection techniques. And at this point, what is going to happen is the FFC will be the one driving the actuator signal. And unlike the feedback control, it's not going to wait for the drone or the RV to move out of the trajectory. It's going to proactively apply the control signal even before it deviates. And when the attack subsides, we go back to the feedback control because that's the time and tested technique. So there are a number of other details I'm not presenting here, but I'd be happy to chat more if you're interested. So how did we measure all this, or how did we test this? So our system, we call it Pied Piper or PID Piper, because PID controller. So the idea here is we go to plug this in directly into the robotic vehicle autopilot software, into the firmware, and we're going to run this on board. So one of the challenges was we have to make sure that our overheads, both performance and energy overheads, are low enough that they satisfy the real-time constraints, as well as don't cause battery drain. And I'll show you later that we achieve these objectives. But at a very high level, we train these models, and then we convert them to C++ and plug them into the firmware. And we have a whole bunch of different RV missions to train: circular, polygonal, straight line, and so on. And in our paper, we talk more about how much training you need to get a stable set of missions. So these are some of the robotic vehicles we applied this to. Actually, there's a fourth one which is not here as well. So there's the custom-built drone. There's one Iot rover that we bought online, and another drone. So one of the challenges I'll say in this domain is we end up breaking these things a lot because for obvious reasons, when we crash and so on. So we wanted vehicles that are not too expensive, that we can fix on our own or 3D machine the parts if they're broken. And my students actually came up with a way to do these experiments without too much damage. So one thing which we also have to worry about here is how do we categorize a mission success? Because remember, our goal is to ensure that the drone actually reaches its destination, right? But like with all physical phenomena, you can't really pin it down and say it has to reach exactly that. So we said if it reaches anywhere within 10 meters of the destination, we consider that a success. So we might say, why 10 meters? Because the standard GPS error is 5 meters. So 5 meters for the drone and 5 meters to the destination. So if you're within a circle of 10 meters, you can't distinguish a GPS, just a regular GPS error from reaching the destination. So the first thing we did was to compare ourselves with prior work. So there's only one other technique that does recovery, which is called SRR, that appeared last year. And essentially, they have a physical model of the environment, and they try to do recovery on top of the PID controller. So this is the feedback-based control. And ours is, of course, PID Piper, which is feed-forward control. So we first run the drone missions without any attack. So this is just regular, fly the drone and see what happens. And with SRR, recovery was activated 20% of the time, but only about half of the time they were successful in the mission. So even without any attacks, they had a crash of about 10%. So the false positive rate was 10%. In our case, we did have false positives in terms of recovery being activated, like with all machine learning techniques, but the recovery was successful. So we never had a failed mission. So at worst, what will happen is the feed-forward controller will take over and steer the drone to its to the correct trajectory. So we had no failures, and so our false positive rate is 0. Okay, that's the first comparison. Then, of course, we tried launching different kinds of attacks. So here we used prior work that had come up with multiple attacks, and we considered 3 kinds of attacks. So we also looked at stealthy attacks, where the attacker is trying to avoid detection. I'm not presenting those results here due to lack of time. But what I'm showing you here are attacks which were going to cause pretty large deviations, and without any protection, the drone will almost certainly crash. So when we deployed SRR on these robotic vehicles, only in 13% of the time was the mission successful. Meaning only 13% of the time it actually went near the destination within 10 meters, the 10-meter radius. With Pied Piper, on the other hand, the success rate was close to 83%. So in almost all the cases, we reached within that circle. In fact, even when we didn't, we narrowly missed it. But of course, to be fair, we didn't change the definition. So we might have been 12 or 30 meters away, but we still count that as a failure. Which is worse, in 50% of the missions that we did with SRR, the drone crashed. So even though it was supposed to recover, it would crash, and of course that's a mission failure. My apologies. So that's 37% of the time mission crashed, not 50%. So 50% there was no crash, but the mission failed, meaning it didn't reach the destination. In 37% of the time it crashed. With Pied Piper, it never crashed. We did like close to 100 missions. We never found a single crash. And in 17% of the time, which is the complement of this, we found that it deviated and didn't reach the destination. Okay. The final piece of the puzzle at present is the overhead. So, like I told you, one of the challenges was to make sure the overheads were low enough to satisfy the real-time constraints. So these were running typical embedded microcontrollers like ARM and so on. So we didn't have a lot of computational juice available to us, and they were running embedded Linux or embedded RTOS. So we had to make sure our implementation didn't violate the real-time loop the robotic vehicle was following. And on average, our overhead was about 7%. We never missed any deadline. So if you just look at the end-to-end time, you can't tell that a technique is even running. But if you go and actually measure the CPU overhead, there was a spike above about 7%. This led to about less than a 1% increase in battery time. So this is important because you want to optimize for battery time in these missions. So we think it's a reasonable trade-off for 1% battery time overhead to get protection against these attacks. And like I said, the mission delays were pretty much non-existent. So I don't want to stand here and claim that we have solved this problem completely. There are actually other kinds of attacks that Pied Piper will not be able to handle. In particular, for example, simultaneous multiple sensor attacks, which have been shown to occur. And the reason it can't do that is we assume only one sensor is attacked right now. So we are working on this new approach called DeLorean, which is trying to recover from multiple sensor attacks. But of course, there's some assumption you have to make. So we assume the attacker is confined to a certain geographic area, so they can't attack the whole mission, right? But our key idea there is to use online diagnosis using something called factor graphs to find the attack sensor, and then use state replay using historical states to override these faulty sensor inputs. So we find that this is also pretty good in terms of recovering the drone, not as high as Pied Piper, but it was over 60 to 70%. So in summary, the work I presented today, Pied Piper, which is a way to recover from attacks, provides attack recovery. It prevents crashes, no crashes, no false positives either. And sorry about that. And it ensures mission success despite the attacks. And the performance overhead was only about 7% on average, 1% energy overhead. More information in our paper that we had at DSN last year. And the code is available. Of course, we only run it on the 4 robotic vehicle systems I showed you, but you can try it on others. And if you're interested to watch some cool videos of how Pied Piper recovers from real drone attacks, you can go to this QR code on the slide. Okay, that's it. And I don't know if I have time for questions, but I'd be happy to take them. Thank you.
So our next presentation is from Dr. Catherine Gabotis, who is a professor at Department of Electrical and Computer Engineering at University of Waterloo. She's the author of Security in Embedded Devices, which published from Springer in 2010, and sole inventor of several patents and widely published in the area of embedded system security, including fault injection, attacks, countermeasures, side channel analysis.
Security is increasingly widespread in many embedded systems, but we have to make sure that the security is not only implemented correctly, but it's also resistant to attack. In particular, this talk will focus on the side channel attack. There are 2 kinds. One is the passive and one is the active. If looking at the passive side channel, for example, we would be measuring the electromagnetic waves emanating from the device. This is largely a well understood area. We have very good countermeasures, patented software countermeasures, as well as hardware countermeasures. However, this is not true of the active side channel analysis. In the active side channel analysis, we're referring to fault injection. Here, even the fault injection model is not well understood. However, these attacks are low cost, non-invasive. They can be performed with the device or even remotely. So there is a definite need to develop efficient countermeasures and improve our understanding of the active side channel. Let's take a look at the history of the fault injection attacks. Perhaps in 1960, one would say, was the very first electromagnetic fault injection attack. Here, the electromagnetic signal was actually an audible signal of a certain frequency obtained from a whistle found in a cereal box. And the actual device under attack was the analog telephone. And the sound of the whistle caused the telephone to enter an operator mode so that the attacker could make any long-distance phone call without being charged. Since then, we've had a number of other fault injection attacks, such as very famous from the Riskier Research Group, bypassing a secure boot, even attacking crypto wallets, such as our next speaker, as well as this year, it hit the headlines because the crypto wallet contained 2 million Bitcoins. Also, other fault injection attacks on the Apple tag in 2021, as well as PlayStation. These are all fault injection attacks. It was even shown by researchers last year that these fault injection attacks could be performed with software, strictly software, sending commands to the power management unit of the processor to reduce the voltage of the core in the processor and inject faults that way. Or AMD's secure circuitry was under attack also from fault injection. It's even been proposed by researchers that field replaceable units, such as replacing your touchscreen on your phone or other components of many devices, could be replaced with a malicious electromagnetic fault injection circuitry, which could then be used to attack the device and send the information remotely to the attacker. Hence, there is a definite need for efficient countermeasures because these fault injection attacks are real and easy to launch and could have devastating impact on the devices and its security. So let's just take a look at what we have in our research lab. We've been looking at electromagnetic fault injection for a number of years now. We actually use the CNC milling system to move our probe around, position it over our device under attack. We have our pulse, which we generate and send to the probe. The probe creates our electromagnetic pulse wave, which injects the fault into the device. So here's a picture of the RISC-V chip, which is what we're going to focus on for this talk. And you can see on the left-hand side, there's a gold coil of metal. This is our electromagnetic fault injection probe, which is attached to our CNC milling system. So we've automated this. This is inside the RISC-V chip, looking through the backside of the silicon using infrared camera. It's 180 nanometers. And this is a view of the actual voltage part of the pulse, which is generated by the electromagnetic probe. The probe has a connector which allows us to measure the voltage. On the left-hand side, we have roughly a delay from the trigger to the actual generation of the probe of the electromagnetic pulse. And on the right-hand side, we have our jitter of the electromagnetic pulse, roughly 12 nanosecond jitter. And so our first objective was to figure out where we can actually inject faults into our RISC-V chip. And so we just used very simple software here. We have this sum test where we increment the value in a register 300 times just to make sure that our electromagnetic pulse will occur within this period of time. And we used our CNC milling system to move the probe around the chip. And if there's no color on this shmoo plot, that indicates that no faults were injected. Where there is color, the darker the color indicates the more faults that were injected. So you can see that when we use 170 volt for our generating our electromagnetic pulse, we get more faults injected. This is not surprising. This is running with our RISC-V chip, running at VDD of 1.8 volts and 320 megahertz. We then also wanted to check out the RISC-V clock frequencies to see what impact that would have, and we showed that if at a higher clock frequency, we get more faults injected. And furthermore, the lower value of VDD, we also get more faults injected. So really pushing the device to their limits. All these operating parameters without fault injection work completely functional in the RISC-V chip. So, so now we know exactly what parameters we want to set our device to, and so now we're going to show you the experiment we used to determine the timing of our target instruction. Here we only have one add instruction now, so this is our target for the injection of the fault is the add instruction, and we're actually moving it for each experiment by placing 101 NOPs before the add all the way up to 120 NOPs before the add. So each of these values of X are an experiment, and we want to see how many faults were injected. We chose the actual position of the chip which provided the largest amount of injected faults for this experiment. So that was using pulse voltage for the electromagnetic pulse of 170 volts, a 1.8 volt VDD for the RISC-V chip running at 320 megahertz. So at each position for the target add is represented, the number of faults injected is represented by the bar in the bar chart here. So for example, the bar on the left-hand side in the bar chart is when we used 101 NOPs before the add instruction. And the bar on the right-hand side is when we used 120 NOPs before the add instruction. So you can see the highest bar indicates the largest number of faults were injected, which is roughly in the middle of the bar chart. The green color indicates that the fault was a skip of the target instruction. The orange indicates that the target instruction had corrupted data. And all the other colors, such as the red and grays and blues, etc., indicate that exceptions had occurred. And so roughly 96% of the exceptions were illegal instructions. And in the RISC-V, it told us exactly what the illegal instruction was. It was all zeros, which makes sense because the NOP we were using was all zeros except one bit was a 1. So it's likely the fault injected flipped the bit. And however, 2% of the exceptions were store access faults, and we were not doing any stores. And 2% were breakpoints. So these were also unexpected. Exploring the faults injected for other target instructions, we looked at the add, subtract, and or XOR, and they were all very similar. In 26 to 33% of the experiments, we saw that the target instruction was skipped. 5 to 12%, the target instruction was corrupted, the data was corrupted, and 0 to 3% ended up in exceptions. By the way, each experiment each instruction involved 1,000 fault injection experiments. So with the load word store word, we also had similarly skip, corrupt, and exceptions observed. However, the store word, interestingly, never, out of the 1,000 experiments, never corrupted the data. The jump and link was also interesting, JAL and JALR, because out of the 1,000 experiments for each of them, the skip in target instruction was never experienced also. This is unlike previous research, which typically always likes to assume the fault model is a skip instruction. Interestingly, with the JAL and JALR, 26 to 30% of the experiments injected a fault which showed the return link was corrupt, and 15 to 16% of the time showed exceptions. Branch not equal, when the data was such that the branch should be taken, we showed that the experiments showed that, again, a skip instruction was never experienced. And in fact, only 4% of the time of the experiments, we had faults injected, which were exceptions. So this only had exceptions, which was surprising. For branch not equals, where the data was a correct data would have been not taken, interestingly, 19% of the 1,000 experiments were false jumps. In other words, it took the branch. So this is also, again, unexpected but interesting data, and unlike previous findings and not supported by previous countermeasure. We also wanted to run an experiment to see if we could skip more than one instruction. So the multi-add test is shown here, where we actually have 10 target instructions. Each of them are add instructions, but the destination register is different, so we can determine if a fault was injected in each of these instructions separately. So our experiment results are shown below, where the x-axis refers to the number of faults which occur at once. And you can see that the red bars are, we have red bars at 0, 1, 2, all the way up to 6. So this means we had up to 6 faults occurring at once. The purple bar is representing X number of faults, at least X faults occurring simultaneously. So we can see that the probability for 2 or more instruction skips was actually higher than the probability of no instruction skips and only 1 instruction skip. So it was more likely to have 2 or more instruction skips, which is again very interesting. We were among one of 2 research groups to show that electromagnetic fault injection could actually lead to more than one fault being injected in the system. So this is quite interesting. Again, it's also interesting to note because current countermeasures only have been developed for 1 skipped instruction, and more recently some software countermeasures were developed for at most 2 skipped instructions. So with these faults shown below, we currently do not have any efficient countermeasures for these. So in summary, not only are electromagnetic fault injection attacks low cost, easy to launch, and can be done with the device or remotely, but more importantly, we have no efficient countermeasures for these attacks, apart from random delays, apart from strictly countermeasuring 1 or 2 skipped instructions, etc. So we really need to have, first of all, a better understanding of these faults. What part of the hardware is susceptible to fault injection? What is actually happening in order to get these effects? So we need full observability of all the stored bits, including pipeline registers, internal control registers, and bits. We need to really get to the root cause and stop treating the actual symptoms. So not only is open source ISA the key, but also open source hardware. So I can only conclude that we should be developing an open source common platform for advancing countermeasures to thwart fault injection. Thank you.
Thanks, Kathy. So moving along, our next speaker is Dr. Colonel Flynn, who you've already heard from a bit. He obtained a PhD in electrical engineering from Dalhousie in 2017. And during his PhD, he also started New AE Technology, which worked to make tools for embedded security more available to both academia and industry. After his PhD, he worked as an assistant professor in cybersecurity and has published both academic and industrial articles on the topic of embedded security, including conference and journal papers, granted patents, and 1 book. He's been on numerous program committees for academic conferences, given presentations at industry events, and is on the Canadian ISO Mirror Committee for Information Security. His past experience beyond this security focus includes embedded system design, IoT wireless protocol development, FPGA design, and PCB design and layout. So go ahead, Colin.
All right. Yeah, thanks very much for having me. So hopefully this is interesting. I kind of wanted to talk a bit about a few sort of open problems in hardware security research that I saw. So there was actually some interesting discussion in the chat, and Dr. Gabati's mentioning about this question of, understanding what the faults are. So that's a really good example of a kind of worldwide open question that's very tricky to answer because, as mentioned in the chat, once you start adding stuff, it maybe is interacting with your results. So that's kind of where I'm coming from. So as mentioned, I started this Chip Whisperer project, so I'm going to be using Chip Whisperer as some of the examples. This spun out of some PhD research, or spun out of my PhD research, and it ties a bit in with CMC, right? Because the question I was having at the time was needing tooling to do the research. My answer was I ended up sort of building my own out of FPGA and ADCs, and that's so slowly spun into a much bigger project. And it's been cool to see because it's now been used in quite a few universities, both research papers, undergrad, graduate programs. And I don't know exactly, but there's at least 100 papers kind of where people have used Chip Whisper as part of it, not just referencing it or referencing a result, but actually, you know, independently of me, not people I'm associated with that have decided to use it. So the real objective of it has been to make all of this stuff more accessible to, you know, researchers in any form. And the point of this talk was I thought it was interesting, especially for the Canadian research sort of community, to talk a little bit about, you know, you have all this experience and there's a lot of people with extremely relevant experience in VLSI and FPGA and semiconductor physics in all of these different areas. And maybe they just haven't, you know, been exposed to the cybersecurity area as much, or hardware security, whatever we want to call it. And so I kind of wanted to bridge a little bit of that gap. And it's going to be quite a high level, very quick presentation. But one of the points of this is that if you have, you know, these different experiences, they're going to bring a lot to the area. And you may actually find that it's not that difficult to get into hardware security. And there is quite a bit of really interesting problems that are kind of waiting for someone who has perhaps, you know, that experience with VLSI and FPGA, and they could help answer some of these questions, or someone with experience on the semiconductor physics side or the communications theory. And as a really simple example of this, one thing I like to show is this, this old school, new school connection, as I call it. If you look at the start of passive side channels, which as an example uses the power the device is using at a given instant in time to help understand the data being processed internally. One of the big jumps in making this very effective and very you know, quick at recovering keys, and I'll do a really quick demo of that after, is what's called correlation power analysis. And it basically takes advantage of the fact that as you move data over a data bus, the power used is very linearly correlated with the Hamming weight, the number of ones in the data bus. So this was an example I took where you can see the current measurement on one axis, the Hamming weight of the data, and except for a little weirdness at the end due to my sample size, it's extremely linear. So it works very well. Now, the funny thing about this is that if you look through the paper, it uses sort of a classic correlation equation to correlate the power measurement with a guess of the Hamming weight. And the attack basically works because you iterate through every guess, and the guess is just one byte. So it's very reasonable to iterate through. And you simply look for the linear correlation to discover the key. So this was published in 2004, relatively recently in academic land, let's say. But if you look at the problem and you look at the derivation, it's exactly the same as a matched filter, right? Where we are trying to recover from a noisy channel what the original sent message was. And this goes back to 1943. And so this is where I say there is a lot of very interesting overlap. So if you're coming from these other fields, you're going to bring a lot of new perspective, or a lot of things that you're going to think are obvious. That someone like me coming from, say, the electrical engineering, more embedded design side hasn't thought about, or isn't as familiar with, or it takes longer to get there. And in fact, this original paper from 2004 on correlation power analysis doesn't even kind of make the match filter link. It sort of reinvents the problem, based on the correlation method, but the actual derivation of what the match filter ends up and what that attacks correlation power analysis algorithm ends up at is exactly the same. So it ends up at the same results. So I'm going to talk about, sort of jumping ahead to current, the following general categories of open problems. So a little bit about fault injection and physical effects, a little bit about power analysis, a little bit about countermeasures, and finally, some deep learning opportunities. So the final one's probably more suited to computer science, but it's a very active area of research. And there's, again, quite a bit of opportunities for extending some of this work in that. For each of these, basically what I'm doing, at least for the first two, the last two I don't have demos for. I'll show some short demos The idea being to show you that, that there isn't necessarily a huge requirement for equipment to get involved with this, or it's likely stuff you may already have in your lab in some form. So the first thing I'll talk about is fault injection, which we just saw a really nice example with RISC-V devices using electromagnetic fault injection. So with electromagnetic fault injection, we're basically generating a very strong electromagnetic pulse. This induces voltages in the actual device itself, which can introduce various faulty effects. There is still quite a bit of open questions, as was already mentioned. There's been some recent work, but it's a tricky problem to solve, is the physical causes of the actual fault. So could we model this in a way that would help us understand how to detect, how to protect these types of faults? The countermeasure and detection is still quite young, especially compared to other areas of research, because there's more kind of ad hoc discussion around what sort of countermeasures make sense. As we were just talking about, there isn't a really good model, isn't a really good way of understanding the exact causes that we're seeing. So we still see quite a bit of papers trying different countermeasures and trying to break them and things like that. There's less fundamental work on it. We also have stuff like, could we do this in code? So there's been work on the question, could a compiler add some countermeasures? And also the question of equipment is an interesting one. So this is two different pieces of equipment, and I don't know if we'll come through. I have a little camera, but one, this is stuff I've designed. So there's a more expensive and this more recent, really cheap one. And what it looks like, right, is that if I have a device is charging up a capacitor bank internally, and we can do stuff like we could take a board. So this board here is running a really simple loop. Let me just reset it. So you can see there's a loop counter that's incrementing. At the same time, it's doing a multiplication and giving a result. And if we insert into the microcontroller at the back, electromagnetic pulse, what we might see is it'll either crash, or in this case, what's happened is it's done an incorrect calculation. And this code is just set up to mark whenever there's an incorrect calculation. If we do it again, like maybe I'll hit it wrong and it'll crash or things like that. Okay, so there's a crash. So it's relatively straightforward to perform these. Then obviously the work is in scripting it, setting it all up. But it's not only electromagnetic, there's lots of other fault injection methods. So as another example, I'll run. So this board is a chip whisperer light. So this was an open source project I started that basically has a target on one side that can be used for power analysis and fault injection. I'm just going to do a really quick example of using, where is it here? Using clock glitching. So with clock glitching, we're purposely inserting sections of a clock pulse that are too short and basically come too soon after the previous clock edge, or to the next clock edge. So you're disrupting all the various setup and hold times that your nice digital logic is expecting. And it's just a really quick example. What happened? Let me plug this in. Wrong cable. Plug that into the right cable. As a really quick example, what I'm doing is I'm just compiling some firmware on this thing. And it's basically going to do this evaluation where it runs that same sort of loop that I was just showing you. And I just want to get it to the point that it's starting to run. And what it's going to do is it's going to try different settings for the clock. And we'll see either red X's when the device reboots, or these green pluses where there is a fault that did not crash the device and just disrupted the calculations. So in this case, it's an instruction skip or something like that. So I'm not tracking exactly what happened in this example, just that something happened. So you can see, it's relatively quickly to get up the basic experiments. And then from there, we can start looking at these other questions about countermeasures and how we understand what the device is doing itself. There's lots of interesting work on using faults for breaking cryptographic algorithms. So the fault attacks on RSA have been known for quite some time, and this is a really easy way of recovering secret keys, with RSA. Okay. A related area is safety engineering. So this is another one where, I think people have experience in this from a different perspective. And so there was a famous case where some Toyota cars were seen to do this unintended acceleration question. And basically, you can use some of these techniques to actually trigger safety critical design. So this is another nice overlap of security engineering and safety engineering. And this goes into the questions of code and how you understand what the faults and things like that are. The other area of this passive side channels is power analysis. So if we look at power analysis, I mentioned really quickly, we're just fundamentally looking at the power as the device is running different operations. So as another example here, what I'm going to do is use on the lower part of that slide, there's a little board with a tiny little chip on it that's actually a small FPGA. And what we can do is stuff like use a, where is it here? I can use a soft core RISC-V processor. So I'll have a soft core RISC-V processor. I'm then going to load a, I'll put that back up. I'm then going to load onto that soft core a AES algorithm, right? And then we can actually do the same sort of analysis. So I'll run in real time. This is just capturing the data. And so this is cool because now we can start looking at, well, what if you want to change the design of the core? This is a totally open source RISC-V processor I'm using here. So you can recompile, not only the code, but the actual FPGA design itself. And then in this case, we just run a really simple, super classic attack to recover the key. But of course, the other area of research is on the attacks itself. Right, so there's all sorts of questions around how do we improve the measurements, like using MIMO techniques, going back to communications theory. How do we do leakage evaluation, before you have chips, if you just had a design for a chip, and also applying this to all sorts of new and novel algorithms. The last two ones I won't do demos for, but other really interesting areas of research, countermeasures, of course. So breaking, it's really fun showing how it's broken, but obviously, for the improvement of the Canadian public safety, let's say, what you want to do is actually show how you should fix it. So the design of countermeasures on both fault and passive side channels is very important. These examples here are some FPGA boards that I designed that are basically specific for doing this sort of evaluation, sort of measurement ports for doing this type of thing. But even there, right, there's a lot of interesting questions that people like CMC can help answer, because one of the open areas is, we can do these experiments on FPGA. How does that translate to an ASIC? How does that translate if you're using different types of cell libraries? So there's all sorts of questions there. And also going into the evaluation of them, as we were discussing, the side channel area has some evaluation. When we look at passive side channels, when we look at fault, it's less clear. Final area is deep learning has become in most areas, right, but also in cybersecurity and hardware security, a really important area of research. And this is quite interesting because with a lot of these attacks, we can generate huge data sets, right? So we don't have to go out and take pictures of thousands of stop signs to get a stop sign. We can do these experiments at my desk really quickly. And so this also brings up questions of, generation and sharing of huge data sets. There's been some work in, the academic community on this, but obviously there's always overhead involved in that, and question of who will support it long-term. Deep learning has mostly concentrated on power analysis that I've seen. There's probably quite a bit of interesting work to be done on could this deep learning be used to optimize the active side channels and fault injection type work. So there's quite a few, very wide open areas in deep learning, even though it's been explored for the power analysis side itself. So I know I covered quite a few different areas. Hopefully this gave you something to think about. Hopefully one of these areas is something of interest to you and kind of piqued your interest. And you can see that there is existing Canadian expertise. I think that's the really exciting thing too. So Dr. Gaborois is on, some of the original work involved in power analysis. So if you look back to where it started, you'll see that people have been involved in this since the beginning of this type of effort. But we can also help build a bridge from research in other areas that might be interested in cybersecurity for all sorts of reasons to further strengthen our sort of Canadian cybersecurity expertise. So if you ever have kind of questions on that, feel free to drop me a note as well. If you have a experience in one area and you are curious about that, I'm always happy to help other Canadian researchers here. But yeah, with that, that's kind of where I'll stop.
Great, thanks, Colin. Keep moving to our next talk, which is Dr. Mitra Amir Hassani, who's an associate professor at the ECE department at University of Windsor. Her research interests include hardware security, Trojan detection, and quantum safe encryption. She and her team are investigating a range of hardware security issues, such as detecting malicious Trojan hardware, efficient implementation of post-quantum algorithms, and implementation of public unclonable functions. She's a senior member of IEEE and is serving as the associate editor of IEEE Access Journal and guest associate editor of IEEE's Transaction on Computer-Aided Design. She's co-founder and co-director of the SHIELD Automotive Cybersecurity Center of Excellence. She's also the advisor of the Women in Cybersecurity Windsor chapter in 2019 and won the Leadership Award for the group's activity in promoting the field in 2020. And was recognized as one of the top women in cybersecurity by IT World Canada in 2020 and won the 2020 Outstanding Achievement Award and Leadership Award in Cybersecurity in 2021 from the APMA Cybersecurity Institute. So Mitra, please go ahead.
Thank you very much. Just checking to make sure that my screen is visible.
Yes.
Right. So today actually has been, thank you for CMC for, for this event. Through being active in this field, I know many of the speakers by reputation, and I'm very happy to meet some of the heroes in the field. So I only picked a very high level top, view of the Trojan hardware, which is kind of a newcomer to the field of cybersecurity, especially for the hardware security, and one that is taking away some of our comfort and confidence in, hardware. We always, in my field, we always promote hardware as the well, we promoted more than software, to be honest, in terms of its reliability, in terms of its acceleration, but and software has always been under review in terms of the adversarial attacks and some of the features that happens to the software. But with the Trojan hardware, we are losing some sleep. So maybe today's session will encourage and maybe even, who knows, create some collaborations on this field. And okay, so I'm actually I was doing mostly research in neuromorphic engineering, and was building chip after chip using CMC resources and services to fabricate hardware development in terms of the highly parallel device computations in hardware. However, over the past few years, we've been, focusing some of our efforts more towards the Trojan hardware reliability, and hardware security. So what is actually happening in the hardware? So as you guys know, when we build the hardware, we send it to manufacturing, and we receive it. Or we buy even some of the embedded platforms, various FPGAs, various processors, And we usually do test them in terms of functionality. Some of the processes, if it's ASIC, we tend to go more deeper into knowing what exactly we implemented, tend to do more rigorous testing to make sure that the hardware that we ordered is what we actually wanted. But more and more we see that more threats are coming from the way that the supply chain for hardware works. And when we think about the field of automotive cybersecurity as one of the fields that we are interested in, we are working especially, the big problem that coming their way and that industry, the OEMs and the suppliers, is not from the software imports, but it actually comes all the way from the hardware, the movement of electrons, the way our transistors are fabricated. So the authenticity and basically integrity of our hardware is under threat. And when the hardware is attacked by the Trojan hardware, it actually is sometimes not distinguishable even from the faults. So the receiver is not even sure if the hardware is faulty or if it was a one-time glitch, because after that, the hardware can actually seemingly do what it's supposed to do, with maybe if you keep monitoring it, detecting some activities that you didn't anticipate to take place. But however, they are very wide, varied, and changeable, the Trojan hardwares, and they are not that easy also to be found or detected, either through the dynamic measurements, side channel analysis, or functionality tests or anything like that. They are generally very challenging for us to find and detect them. This Trojan hardware, the modification happens not to any of the instruction sets, but actually happens to the way the transistors work. It can be a bunch of transistors that are basically placed within the hardware that are very hard to catch, or they can be some modifications to the nature of the transistor that is already in the system. And by that, I mean, for example, changing the material property at the fabrication center. So basically what it does, it can have a very wide or again, very different nature of payload. The payload can be very different. It can be, for example, to stop the operation of the IC. It can be used for leakage of information. It can cause glitches at parts of the program. As well, it doesn't have a set time of activity. I mean, the Trojans can become active at one time randomly, or depending on some clocking activity, they become active. So even the mechanism, the trigger for the Trojan is not set, and there is no way. Basically, the Trojan hardwares are as wide and varied as the human mind and imagination can go. So the designers, everyone that is in the process of design of a hardware can be party to this malicious act and create one form or another of the Trojan hardware that is getting activated or triggered in a different way, and it brings different payload. So the field is very wide open and actually requires attention, as we can see now with the coming 5G, with the coming of the connectivity and vehicles, infrastructure, V2X, everything. These can be our next problem, especially if we are placing, or if you're thinking, for example, of the vehicle, because I'm in the automotive side. If you think, for example, for the trucks, or buses, transit systems, these are not one-time purchases or investments. These are long-term investments. If you're thinking about the battery, infrastructure, the EV chargers or power infrastructure, because this hardware can be used everywhere for every application. Therefore, we basically cannot go in and say, okay, we're going to fix this by a software patch. In most cases, the hardware parts, the whole IC has to be taken out and be replaced by a newer one. Unfortunately, there is no treatment to hardware Trojan as compared to the software Trojan or adversarial attacks on the AI or machine learning. For the hardware Trojan, in at least every case that I know, the only remedy has been to go in, take the part out, and replace it with a trusted component. So, as I mentioned, there are payloads of the Trojan are wide and varied. I just mentioned 2 of them, and here's the basic. A very wide or somewhat try to include, mention where and how the Trojan can be introduced to the hardware. It can be, for example, when someone is designing the circuit in collaboration with a couple of other industrial or third parties. It can be included while in the fabrication process. It can be included when the specifications of the design are decided at the high level, at a very, not even at the time that we are not even thinking about the hardware itself. Activation mechanisms can be wide and varied, as I mentioned. So we can see that it can be always on, so it doesn't even show up when we do the side channel, and some of the dynamic, trying to create the or look at the hardware signature, they don't show up. Usually they're also placed on paths that are not accessible all the time by clocking. So we did try to overclock do fault injections and some of that, but we cannot guarantee that we reached the Trojan hardware at all time, especially those that were just waiting for a different type of trigger signal rather than just being there by the clock. So they were also very, very different. So this Trojan taxonomy that I'm providing here is a very high level and actually a very summary of the possibilities. And as you can see, it can be wide and varied and very different type of attack on the hardware. Here's again another example of a couple of these type of attacks. On the right side, for example, you can see that even through the scanning, if you're looking at your device, of course, that's a layout. I understand, just to be clear, that's not a scan of an IC. On the right side, if you can basically see, there is just a material property that is different between the left and right. So the transistor or the whole circuitry might work fine, but even this or a couple of these units can be a trigger to stop the system or the hardware. We haven't published our results yet, so that's why I haven't shared some of our published results. I mean, it's in the process of review, some of them, but the very scary thing was that the clocking systems can be very easily and readily be vulnerable to this type of Trojan, especially if you're considering that we are, for example, buying these FPGAs from vendors. And in most cases, we have no idea what's the clocking scheme on those FPGA boards are. They are highly protected. They're not, the vendors are not sharing the technology, but even the vendors might not be known or privy to the fact that their hardware is compromised. On the other side, you can have a bunch of transistors added to disable portions of the circuit. A thinner metal layer can also be a way that to insert the Trojan. So even someone that is, some of the first solutions been that, okay, we're going to take the layers off of the chips, pick a couple of them and take them through random scanning. But with the current hardware, it's rather a moot point, not possible to detect all the intricate changes in the wiring of the devices that easily and readily. You need a lot of deep learning application to go through the hardware to detect and match the scan with the original IC, and then all the time. Again, that only works if we are the ASIC designers. We are, if we know what we have purchased or what we fabricated design comes from us. If you're buying some of the readily available platforms like the FPGAs, who knows what's actually should be there, so it wouldn't work for those. So the Trojans, the point I'm trying to make is that it's applicable to both ASIC, to hardware, to GPU, and anything that runs on electrons and runs on hardware, and any hardware software runs on hardware. These are open to attack. This graph is some of the ways to test, then try to, basically, I should say, hardware Trojan, not protection is at the lower side. In the current academia, we're mostly on the detection side. The preventions are, to some extent, prevent the currently known hardware Trojans, but we are not even fully covered the various forms of hardware Trojan in order to be able to say that we are being able, or we can propose ways to prevent them. We've been buying the AE from, the equipment from Collins and their lab, and we did try to use different ways of side channel. Some of them work, but hardware Trojans are actually sneakier than to be caught by some of these testing methods, unfortunately. So what we are basically saying that there should be, this is a problem that is has a lot to be explored. No solution has been able to even identify a majority or even sometimes even existence of them, of the Trojans. There has to be, of course, certain steps while the team is designing their hardware. That's open only for people that are using the ASIC design methodologies. Some of the eFPGAs, but not, for example, if it's an embedded system, then the trouble is actually more, is deeper than that. The testing and verifications, of course, are going to be longer if we want to be sure of the Trojans. So we have to actually add more features when we are testing the hardware, not just the verifications of the hardware. And that's actually mostly for the OEMs when they buy an FPGA and they test it to run or program basically integrity and not the hardware. So they just verify the behavioral and then they're good to go. And there is a need for live methods that are actually checking the hardware during its runtime, which is again an added overhead. So from every point that you're trying to attack or look for a hardware Trojan, there is always an extreme amount of overhead so far in most of the methodologies. As I mentioned, they are tiny, they are quiet, there are very different and varied. They depend on the human intelligence that is sitting there and coming with a different malicious way of inserting. So far, the very conventional test and fabrication methods have not been very successful to detect the Trojan hardwares. The new challenges are that, as I mentioned, if we had a trusted center for the hardware fabrication and a trusted center for purchasing our hardware from vendors, that could have been helpful, but as of now, we don't. Even when we think that we bought a part, or an FPGA from a vendor, rest assured, it's not all been done by that center. It can, come from different manufacturing lines. It goes back and forth between the third parties, and then we buy that hardware from that specific vendor. As I mentioned, the second, one of the most recent discoveries is that even the doping level or metal, metal width. Sorry, I think I said length previously. The metal width of that runs in the hardware can be a source of a Trojan circuit, and they are again, most of the current approaches are relying on having what they term golden IC or golden chip, which is very unrealistic, because if we have the golden IC, then continue using that, services or that line. So most of the papers and in academia and even in industry relying on some huge assumptions that they have access to a golden chip that is free of any malicious entity on it, which is, as I mentioned, very, very unrealistic. So what we are basically doing in my lab, we are building systems with an open eye on the hardware security, but then I'm actually running a blue-red team approach most of the times, where we develop the system, we attack it, and we try to learn the lessons. And basically that approach has resulted in some rather good outcomes, but there is more research that we need to basically undertake for this research. And here I'm going to stop my presentation.
So our next presenter is Dr. Manoj Sachdev from University of Waterloo. He's a professor and interim department chair there in the Department of Electrical and Computer Engineering. His research interests include low power and high performance digital circuit design, mixed signal circuit design, test and manufacturing issues for ICs. He's contributed to over 230 conference and journal publications, has written 5 books, and holds more than 30 granted US patents. He's a fellow of the IEEE and fellow of Canadian Academy of Engineers. Manoj, go ahead.
All right. So today I'm going to discuss reliable machine learning raised and physically unclonable functions, and that me and my colleagues had been working on for some time. Okay. Now, I must acknowledge that really the work is done by graduate students, and professors just give the talk. So 2 of these students, Hugo is a circuit designer or system designer, if I may say, coming with a circuit design and architecture for puffs, while Junhao is the expert on AI, machine learning, and trying to see if we can break these architectures or design. So between Hugo and Junhao, we have a good idea that what is workable, what is not workable, and how can we modify the architecture of puffs in particular. And Dr. Hiren Patel is my colleague professor who has been contributing immensely towards this project. So I have a very simple presentation outline. So why we are doing this? What's the problem we are trying to solve? What is our motivation here? And then in this context, what is the background for physically unclonable function, and where we, in terms of, authentication in particular, puffs can be used. And finally, the architecture that we came up is puff on puff, which is arguably, machine learning resistant and reliable puff architecture. And we'll try to show you some measurement data and analysis to show that really is the case. Okay, first the motivation. What is the problem? As we heard today over and over again that there are billions of IoT-enabled devices that are connected to internet, right? And their security, safety is extremely important. And one of the challenges is that how do we find out, or how do we authenticate a particular device? Is this really my phone, or is this really my device, right? How do we authenticate, right? And traditionally, we had been trying to solve this problem through programming a secret key, okay, such as flash memory or E-square PROM historically. And those keys strings are vulnerable to attack because these are permanently stored in a particular device. And an expert many years ago mentioned that merely calling a bit string a secret key does not make it secret. On the other hand, it rather identifies as an interesting target for an adversary, right? So this doesn't provide any security. And as Mitra and others said that the fake device business is real and big. And so $75 billion of the fake semiconductor, repurposed, reused semiconductors are causing a lot of grief to the various parties. Now, what is puff? Puff in simple terms is akin to your signature. Your and my signature is fingerprint, is unique, right? The same way, this is a digital signature, perhaps can we extract from a chip, any instance of a chip. And now the question is that how unique, how tamper-proof the signature is, right? So the puffs are created a unique device fingerprint from inherent device variation. Even if you try to make two transistors identical on a chip, owing to the process variation, inherent process variation, their behavior may be slightly different. Why do I say that? Because CMOS, or manufacturing process of chips, is one of the most complicated process invented by humans, which may have 500, 600 process steps. And all of these process steps have finite standard deviation or sigma associated with it. Even though you might make identical chips or identical elements in the chip, they will exhibit inherent process variation or differences. And those can be exploited to realize this digital fingerprint. Okay, now the puffs also use challenge response protocol. So essentially, you challenge the puff and puff responds, and then you can determine whether that response is what you expected this response to be. There are two types of puffs. One is known as weak puff, another one is known as strong puff. The weak puff has limited CRPs, or channel response pairs, and this is primarily used for secret key generation that also requires extra hardware or encryption to ensure that this key is stable. Now, the strong puff, on the other hand, has billions or trillions of CRPs, and primarily they are used for authentication purposes, and that's where our focus is. Okay, now how the authentication is performed with a strong puff. So first of all, you enroll the puff. Let's say a particular chip which contains an implementation of puff, right? Now, in a secure, trusted environment, you query the chip against all kinds of challenges, or enumerate all these challenges with responses. So that's how you create challenge response pair in a secure, trusted environment. After that, this particular chip instance is released to the customer, and now it is part of, let's say, secure system. Now, in this untrusted environment, when the server needs to authenticate this particular chip, whether that belongs to my cell phone or that's part of the IoT system that's opening, my front door in the house, that the secure server will query this puff inside this particular chip with a subset of challenges. Okay, and now this puff responds, a puff in the chip responds, and then this is and the secure server sees if this response matches with the enrolled response. If this matches according to certain criteria, then the authentication process is complete. Okay. So now some background on a few different puffs. One of the most popular and earliest puff is what is known as arbiter puff. Now here, these are n muxes, let's say 64 muxes, pair of muxes. This is a pair, right? This is another pair. And this is your challenge space. Let's say 64-bit challenge space. Depending on whether the channel, this particular channel, C0 is 0 or 1, if I give an input here, this will race through whether through this path or through this path. So depending on the strings of zeros and one in this challenge path, I may have, for 64-bit challenge, I may have 2 raised to the power 64 unique paths or delay paths. So the argument or the thought is that each delay path is a little bit different compared to others. Okay, and so now at the other end is an arbiter. Here, a simple D register or D flip-flop, right? So depending on whether the data comes first or the clock, this response will be 0 or 1. And that's how, with respect to these challenges, a particular response, which is 0 and 1, is secure right here. Okay, so this, what is the challenge, and this is what is the response, right? Challenge, response, pair. Now, the question is it secure? So in some sense, this is not. Only with a subset of challenges, challenge 646 CRPs, one can model the behavior of this, puff with greater, confidence, 95% confidence. So essentially, this puff is broken because an adversary can learn how the relative delays are. So then this puff can be mimicked by, let's say, some other system or some other software, which is mimicking the behavior of this puff. And the security features of this puff are no longer valid. Now, researchers over the year, they come up with a better architecture, such as, the feed-forward arbiter puff. So essentially, make it a little more difficult, or multiple puffs, which are, XOR. So the response is a little more obfuscated from the, the challenge space. However, all of these can be broken with little more difficulty, right, compared to the previous one. However, the problem is that this is no longer can be used for a security purposes. And these are, essentially, are doesn't meet the quality requirement that we expect from a puff. Okay. So here, we proposed something a few years ago where you have this original puff, and now these are the challenges. So what we want to do is these challenges should be one-to-one transformed from the initial challenge space to a transformed instance-specific challenge space. Okay, so the first layer of puff transform the challenge from the original challenge to another 64-bit challenge, which has one-to-one mapping, which is also instance specific. What do I mean by instance specific? Essentially, if I have two instances, two implementation of or two different chips of the same architecture, so the intermediate, the output of this first stage, right? First stage of puff will be two different things for two different implementations. Okay, so that's what I meant by instance specific challenge transformation. And this was presented a couple of years ago. Okay, now the other feature that we implemented in silicon, thanks to CMC, is that how do we make it more reliable? So we did a couple of things. So one was that, this is the original arbiter puff, and which includes, the arbiter here, which is regenerative feedback path. Now, one of the problems with this architecture is when these two signals are coming very close to each other. Let's say, sub 10 picosecond delay, which is quite often. This may this arbiter may not be able to resolve whether it is 0 or 1, and this problem is well known. It's known as a metastability problem, which is inherent in every such regenerative feedback architecture. So, which is also illustrated here. So, as these two signals are coming closer and closer to each other, essentially it's taking forever to resolve. If they come at the same time, the X node or Y or the X prime node here will not be able to go to 0 or 1. So the architecture that we came up with, which is, essentially have one more regenerative feedback after this. And this is also used in many, metastably hardened synchronizers. Essentially what it does is that it suppresses the metastable output. So providing, the convergence on Y or Q0 or Q1 a little better. And so the bottom line is the reliability is enhanced. The second thing what we also did was to reduce the likelihood of metastability. You run it at a lower supply voltage for enrollment purposes. So why do we do that? Essentially, if you are, at a nominal supply voltage, this is the Gaussian distribution of the delays, right? Okay, and certain range of this delay, you'll have small enough difference that this arbiter is unable to decide whether 0 or 1, and so that's why it leads to metastable behavior. Now, if you run at a lower supply voltage, the delay distribution, the delay of transistors in a chip is a strong function of supply voltage or overdrive voltage of the transistor. So if you reduce the supply voltage, or if you reduce the overdrive voltage of a transistor, its delay increases. Now, if it increases, and that will lead to a distribution something like this. So essentially, we can reduce the occurrence of metastability probability substantially. Okay, and this was the theory, and these were the measurements that in 65 nanometer we carried out measurements. So what we did, essentially, we put the two delay lines like this without an arbiter in a chip and brought the chip outputs outside the chip and connect an oscilloscope to these two outputs, differential or these two outputs. And these are the measurements. So at a lower supply or higher supply voltage, you have, let's say, this typical distribution, right? And if you can reduce the supply voltage further, in this case, 0.3 volts to 0.2 volts, what you see, the distribution widening out. And consequently, you can, reduce the probability or likelihood of metastable behavior or enhance the reliability. Now, if you reduce it too low, the thermal noise also starts to impact the behavior of of the delay. So it's not that you keep on reducing and things will improve. Now, we designed a 65 nanometer test chip, as I mentioned, and then we ran it over various supply voltages. So if you see overall, there are few figures of merit for a puff. One is the reliability, okay, which is illustrated here as a function of supply voltage. Other one is a uniformity, which is the intra-Hamming distance within the puff. Okay, what's the intra-Hamming distance? The occurrence of zeros and ones, okay? And ideally it should be close to 50-50, right, or 50%. And the third feature is the uniqueness, which is the inter-Hamming distance. If I have two instances of puffs, so instance number one, instance number two, how unique these are to each other, okay? And once again, the closer to 50% is ideal, okay? So first, what you see is that as I'm reducing the supply voltage, there's a modest increase in reliability, or 1 minus reliability, of course, is a bit error rate. So reduction in bit error rate, okay, at 25 degrees centigrade. So this is the box plot, what you see, okay? So it's a modest improvement, certainly. Now, if you run at a different temperature corners, right, minus 35 degrees C or 85 degrees C, how the reliability decreases with respect to the golden signature at 25 degrees, right? And that's what you see here. Now, if you were to compare itself over the same temperature, right, then you'll see reliability improvement much more substantial. And these measurements were done over 5,000 challenges, and each challenge was repeated 1,000 times. Okay, and if every 1,000 times is the same, then reliability is 1, right? And this is what you also see in 10 puff instances, that as you are reducing the supply voltage, right? Again, 10 puff instances, you are achieving more towards ideal behavior of puff. So we believe that the enrollment of puff, which is extremely important, should be done at lower supply voltage. Okay, and this was presented, last year in a conference. Now, the last item I want to also discuss that how do we build the machine learning resistance? Okay, and for that we in that chip we put programmable fabric of 2 layers of puff or puff on puff. Okay, so first layer is here, and this is the second layer. Okay, now, so initially we put a challenge, and what you have in the puff 1, these are the same instance, right? Puff 1 could be 2-bit wide puff, but we have 64 of them. Or it could be 3-bit wide or 4-bit wide. What does it mean? So in other words, the 4 bits of the challenge space are incorporated into this. Another separate 4 bits of challenges of this, challenge, 64-bit challenge were used here, and so on. Or we can have it 6 bits or 8 bits. So that's where the programmability feature of the first layer of puffs comes into the place. So we have 64 of them, And each one of them can be programmed either 2-bit wide, 3-bit wide, or up to 24-bit wide. Then we also want to perform, the temporal majority voting schemes to make sure that when we see the reliability enhancement through the majority voting, and then we can also rotate it many times. So in other words, we can rotate it only once or twice or 3 times to see whether that has also any security implication. So finally, then we get the transformed challenge here, which is now deployed on the second level. And finally, after TMV, we can get the final 1-bit response to the initial challenge. Okay. So a couple of slides on the results. So first of all, what you see is that this is how many times on x-axis, how many times I'm rotating, how many times I'm rotating. So in other words, the whatever response I get becomes a new challenge for first layer of puff, okay, and so on. So what you see, the uniformity, and for all different complexities of first layer of puff, from 2-bit to 24-bit. What you see is that as I'm rotating multiple times, from single time to 4 times, it is opening up. Okay, so in other words, it is becoming worse. So that shows that it is, the new challenge is converging because of the inherent biases of the puffs, of a first layer of puffs. Now, on the other hand, the uniqueness still, remains acceptable. Now, the second slide on this, I want to talk about the reliability using temporal majority voting. So on x-axis, we see how many times we are doing the majority voting, right? How many times we are performing the majority voting? No majority voting till 256, right? And at 20-degree temperature or number of different temperatures here, further increasing the temperature range, what you see is that temporal majority voting does help, but its benefit plateaus somewhere, I would say between 64 and 128 for our architecture in terms of reliability. Now, if you extend the temperature range, of course, the reliability goes down predictably, right? If you extend further the temperature range, it goes down further, okay? So this is no surprise. Now, we also compared this architecture in terms of its resistance against machine learning attacks or strategies. So one of them is the evolutionary strategies for 64-bit puffs that we use and contrasted with respect to our architecture. So other architecture, these are the popular architectures that you could very successfully model them with 95% accuracy. And a puff-on-puff architecture, you could, the confidence level is much lower, 70%. And that was presented a couple of years ago in a conference. Now, in this architecture, we also explored that what would be the number of bits in the first layer. Okay, so for example, we took the 2 extreme to show you here. The first layer can have just 2 bits or 24-bit that we put in the system, and how many times you're rotating, right? And how accurate it is to prediction. So the message, so if I have more complex first layer, such as 24 bits, my prediction accuracy is much lower, which is a good news, right? So my prediction accuracy goes down from 81 to 66. Now, if I have fewer bits, and if you are going through the multiple rounds, my prediction accuracy improves, and that because of the bias of the small number of bits, and that can lead it to non-uniformity in the signature, and that leads to higher prediction rate. If I have large number of bits in the first layer, the prediction accuracy goes down, which is a good news. Okay, so this is a salient features we wanted to share with you. If you have any questions, I'll be happy to answer.
Thanks, Manoj. Yeah, I guess in the interest of time, maybe we'll leave questions to the very end, and we'll move to the next speaker, Dr. Sokpom Ko from University of Saskatchewan. He's the professor and acting head at the Department of Electrical and Computer Engineering and a professor at the Division of Biomedical Engineering at USask. He got his PhD from University of Rhode Island in 2002. His research interests include computer architecture and arithmetic, efficient hardware implementation of compute-intensive applications, deep learning, processor architecture, and biomedical engineering. He's a senior member of IEEE Circuits and Systems Society, a member of IEEE VLSI Systems and Application Technical Committee, and associate editor of IEEE Transactions on Circuits and Systems and IEEE Transactions on VLSI and IEEE Access.
Okay, thank you so much for your nice introduction, Hugh. Okay, so hello everyone. My talk is about post-quantum IoT security today. And I would like to also acknowledge my graduate student for this work. My research expertise is computer arithmetic. So recent years, I'm doing AI Accelerator in edge side in particular because I'm particularly interested in energy efficient computation. And a relatively smaller group than AI Accelerator and processor, we are doing some security stuff. So what I'm gonna do is I would like to walk us through to the general cryptography before I share our recent works related to the topic today. And I would like to conclude my presentation. So the cryptography, that's basically to encrypt the data from plain text to generate the ciphertext. And decryption is reverse operation from ciphertext to plain text. So in modern era, privacy and confidentiality that must be properly addressed. And the cryptography is a method of protecting information and communication. This slide is about the IoT, Internet of Things. It's a new form, typically refers to the billions of physical devices around the world that are connected to the internet. We saw a lot of applications and platforms, including e-health and public transportation, smart home and smart cities. If you see the end node, you will see this type of graph. IoT includes end node, the tiny devices, and most of them do not, unfortunately, have enough resources for security guard. And the number of connected devices to the IoT has been exponentially increased. And so we need reliable security system for this IoT. In the cloud and edge side, relatively high speed cryptography is required. So we need a reliable high-speed crypto system. We can categorize the cryptography into two, symmetric key and asymmetric key. And private key and also public key has been used interchangeably. So symmetric key needs the secret key to encrypt the data and to decrypt the data to get the message back. So examples are advanced encryption standard, IDEA and present. And the other side is a symmetric key. It has a publicly known key to encrypt the data, but for decryption, the party or the people who has only the secret key can decrypt the cipher text. And the examples include the RSA, ring LWE, and elliptic cryptography. I would like to introduce the Schwartz algorithm is to find the prime factors of any integer. So when we have a small prime number, it's easy to get the prime factor, but it gets larger and it's tough. So that's where Peter Schwartz algorithm came in, introduced in 1994. When we use a quantum computer, we can use this Schwartz algorithm to find this prime factors. Now, unfortunately, most encryptions rely on the prime factors in order to be secure. For example, RSA is based on factoring large integers, and ECC is also based on discrete algorithms. So the AES algorithm, Advanced Encryption Standard, standardized by NIST in 2001. And this has been used in a wide range of applications in recent years, in particular IoT and LoRaWAN, and sometimes it is used for generating the errors. And there are no successful attacks against this AES so far. And AES 256 is considered to be secure in quantum era. And this is, I'm sure that the audience knows the way how AES works. It contains 4 main blocks: edge round key, shift rows, mixed columns, and sub bytes. And the number of rounds depending on key and input length. For example, 128-bit needs 10 rounds, 256 needs 14 rounds. Lattice-based cryptography, LBC in short, is one of the accepted quantum-resistant public key cryptography. It has a relatively faster operation than the other example, isogeny, and a lattice L is defined as the set of all integers, linear combinations of n independent basis vectors BI. This figure shows the 2-dimensional, and it can be extended to n-dimensional. Now, it is extremely hard to find the closest vector and shortest vector. Those are called the CVP and SVP. And there is no algorithm, classic computer or quantum computer to solve this problem so far. Learning with error, LWE, is one of different varieties of LBC techniques. A known public A and E represent the error. So it is hard to find the secret key S by adding errors. And since this is the variant of LBC, the shortest and closest vector problems are still there. So thus we can say LWE is really hard. Ring LWE, by the way, LWE used the n by n matrix for A, and ring LWE is more practical and efficient in hardware. And compared to LWE, it does have a smaller key size. In key generation, basically, it is to calculate the public key and the secret key R2. Encryption stage is to generate the ciphertext C1 and C2 using APNM. And the decryption stage is to get the message back using C1, C2, which are generated from encryption stage and using this R2 secret key. In ring binary LWE, this is the new, relatively new variant of ideal LBC introduced in 2016. And ring binary LWE has a binary distribution, which is different than ring LWE as a Gaussian distribution. And the errors are sampled with the binary coefficients, which means ring binary LWE does not require Gaussian distribution and NTT for LWE. So, and the key size is smaller, which makes this ring binary LWE is a very suitable candidate for resource constrained IoT devices. And sorry, multiplication and addition are two main operations. Now I am going to move to our recent works, and unfortunately I can't touch all the details, but I would like to provide the high level ideas of our recent works. The number one is we try to build the lightweight version of AES. As I just mentioned, that AES is quantum resilient the cryptography. So we built the 8-bit Nano AES data path accelerator. So to reduce the area, we use the sub-bytes, for example, shared with encryption and key expansion. And also we optimize the mixed column box and one register banks for storing keys that is named the key register right here. And the other one is for plain text, that's a state register. So again, to reduce the required logic, we shift rows is embedded into this state register. Also, we build our cone block and control unit. And this, to have more details, and you can refer the paper which we published in 2020 in IEEE VLSI. So this one shows the state register with the shift rows. Again, it's embedded to reduce the required logic. It does have a 5 major operation. It can store the main plain text, and it can execute the shift row operation, and it can store the data that comes from mixed columns only in the last column, and feeding the design by one 8-bit, and at the same time, it can store the data. Also, we apply the clock gating technique to save the power. This is the sub-bytes block. We optimize the sub-bytes block using the combination of inverse isomorphic operation and applying transformation. And this is how we actually implemented the sub-bytes into hardware. And mixed column also by simplifying, for example, 3A1 to 2A and A. And we were able to reduce the required logic significantly. And this one shows the block diagram of mixed columns and shows the timing diagram of the proposed mixed columns. And this table shows the implementation result in TSMC 65 nanometer. And as I explained before, due to the techniques that we used, we were able to get the smallest area compared to the similar type of work available right now. And this one shows the area, and this one shows the relative normalized power as well. So this is the first work, lightweight version of AES implementation, especially for resource constrained IoT devices. These are the references that I used in the previous slide. The next one is a post-quantum crypto system for IoT resource constrained devices. So basically, we implemented the ring binary LWE I introduced in previous slides. So again, the most important arithmetic operation is the multiplication. So the straightforward method of multiplication for ring binary LWE is just a traditional schoolbook operation. Each single coefficient of multiplier is multiplied by all coefficients of multiplicand to generate the partial product. And the anti-circular this operation and the reduction occur in each row. This is the key row for partial products, the yellow coefficient. And the partial products are added into the intermediate sum, which is represented as IS right here, followed by modular reduction. And the final result will be accumulated to the intermediate sum, followed by modular reduction. So this is the traditional straightforward method of multiplication for ring binary LWE. In our case, we coefficient multiplication is in a column-wise manner, right? So instead of using row-based one, we use the column-wise coefficient multiplication. So this is the way how we implemented into the hardware with this column-based multiplication followed by in-place reduction and anti-circular rotation, which are pretty much similar to the straightforward method. So now we tested this idea into AGIC. So compare with the recent state-of-the-art work, as you can see, we were able to reduce the area significantly and the power as well. We also tested this crypto system into FPGA environment, and we got the similar result as AGIC implementation. Okay, so this is the references that I used in previous slide. The last one is the lightweight and CCA2 secure implementation of ring binary LWE. This is about fault injection attacks. So data can be manipulated, right, by injecting an error into either memory or signal so that it can obtain the faulty execution of the system and try to extract the message or private key by evaluating the result. So there are three major fault attacks over crypto system: randomization, skipping, and zeroing. So among three, skipping and zeroing has a significant impact on in ring binary LWE. So what we tried in this block diagram, it was hard to put all things together, but let me try to explain the high level concept of this one. Ring binary LWE, this one is the one that I introduced, which was published in 2021 Elsevier Microprocessors and Microsystems. And this AES core, that's 8-bit Nano AES core published in 2020 IEEE VLSI. Now, what we did is we used this AES core to generate the errors. And this is the key M value. M value is from this comparator, basically executable operation. So comparing the ciphertext messages, then we can say whether fault injection happened or not. So this block diagram basically try to add fault resilient countermeasure to our original ring binary LWE system. So this pseudocode shows the ring binary LWE encryption and the decryption stage. And this work will be presented in EASTCast 2022 this May, hopefully in person, Austin, Texas. Also, we implement this lightweight and CCA2 secure implementation of ring binary LWE. Unfortunately, there are not many similar type of works available in the literature. And what I try to say in this table is, for instance, look at the slice number 423 in vertex 7. This is only 1% of the total available logic resources. So with this much resources, and we were able to add the fault-resilient countermeasure to our ring binary LWE. So I would like to summarize my talk today. The number one is, due to the nature of IoT world these days, providing end-to-end security is extremely important. Also, with the quantum computer, most of the current crypto system will be in danger. So now, what are the answers, solutions? AES is secure symmetric cryptography algorithm. And the LBC, lattice-based cryptography, is one of the promising PQC methods. And in particular, ring binary LWE is a suitable candidate for risk-constrained IoT devices. And ring LWE needing Gaussian distribution and NTT is a secure algorithm that can be used in high traffic applications. So we propose the lightweight AES architecture and the lightweight ring binary LWE for IoT devices. And the result shows our 8-bit Nano AES core shows the 22.1% area reduction over the best similar implementation. Also, it shows the very, very good power consumption as well. We proposed a novel column-based multiplication for ring binary LWE. And the proposed ring binary LWE design has improved the area significantly by over 50% and the power by close to 50% over the state-of-the-art design. So according to the result and NIST report, the proposed both AES and LWE core, a ring binary LWE core, are suitable for resource constrained devices. The last one, we try to address the fault attack issue and to increase the security and resistance against the fault attack. Fault resilient countermeasure is added to the proposed ring binary LWE, and we demonstrate that we just need 1% of the total available slices for the entire ring binary LWE with fault resilient countermeasure. This is my group, and I would like to again appreciate their time and effort for this one. And thank you very much for your attention.